Hello, good afternoon, everyone. Let's start the tutorial today. So we are talking about the topics on number theory. And today I have selected a related problem called Chinese remainder theorem. So let's see this example problem. Suppose that someone tells you there is a certain unknown x, and then this x has the following properties. So when it is divided by 3, x is an integer, okay? So when x is divided by 3, then there will be a remainder of 2. But when it is divided by 5, then it will give a remainder of 3. And when it is divided by 7, then the remainder will be 4. We want to know what are the possible values of x. So, and also, can we find a certain x that satisfies this behavior? Okay, so to understand this, so let's take a look of these two important facts. So first of all, suppose that there is a certain x that satisfies all the properties. Then when x satisfies this property, then x plus 105, x plus 2 times 105, x plus 3 times 105, or x minus 105, x minus 2 105, x minus 3 times 105, all of them will also satisfy this property. The reason is that 105, the number 105 itself, is a multiple of 3, 5, and 7. So when x is added by 1, 0, and 5, then in that case, this formula will remain the same. So the value of x after adding 105, and then when this new number is divided by 3, it will still give a remainder of 2. Similarly, when x is added by 1, 0, and 5, then it doesn't change about this equation, and so on and so forth. So we will see that the number 105 is a magic number here, so that when we add a number of 105 here or deduct a number of 105 there, then the resulting value will still have the same property as before. So this is the first fact. The second fact is that for any two numbers, this is like the converse. If someone tells you that two numbers, they are satisfying these properties at the same time. So let's say x has this property, and let's say y also has this property. Let's say y divided by 3 has remainder 2, y divided by 5 has remainder 3, y divided by 7 has remainder 4. Then in such a case, then we will see that x minus y itself, this number x minus y, will be equal to 0 in all of these cases, which implies that x minus y will be divisible by 105. Excuse me. So there is a y here. So you need to convince yourself why this is true. So I will leave this for you as an exercise. So based on these two facts, then what we know is if some x satisfies the properties, then the value of x will be unique under modulo 105. So the problem now is whether x will exist or not. It turns out that the answer is yes. We can actually prove this by construction. So let us do the following 4 steps. What we are going to do here is we take the remainder of modulo 3, so which is 2 here. We multiply this by 70. We take the remainder of modulo 5, which is 3 here, and multiply this by 21. And we take the remainder of 7, which is 4 here, and multiply this by 15. And after that, we add all of them up. So this will be one of the x that can satisfy the equation. So let's see this example. Excuse me. So remainder of modulo 3, which is 2 times 70, and then 3 times 21, and then 4 times 15. We add them all up together. It is 263. We claim that x is equal to 263 will work. And in fact, because we are talking about modulo 105, so 263 and 53, they are the same under modulo 105. So we are claiming that when we plug in x to be 53, then it will work. So let's see 53 whether it works. So 53 is equal to 51 plus 2, and 51 is a multiple of 3, so 53 satisfies this equation. So 53, of course, is a multiple of 5 plus 3, so it also satisfies this equation. 53 is equal to 49 plus 4, so it is equal to 4 modulo 7. So 53 works. And not just 53, 53 plus 105 multiplied with any integer, positive or negative, or 0, it will also be a solution. But then you may wonder, why does this method work? So in order to understand why this method works, let's take a look on the specific numbers that we are talking about. So remember, we are multiplying by 70 for the first remainder, multiplying by 21 for the second remainder, and multiplying 15 for the third remainder. Okay, so let's take a look of these special numbers we are looking at. So what is special about 70? So 70 itself is a common multiple of 5 and 7, right? But then 70 itself is also equal to 1 plus some multiple of 3. Now, if you take a look of 21, 21 is a multiple of 3 and 7 at the same time, and it is also equal to 1 plus a multiple of 5. And 15 is a multiple of 3 and 5, and it is also 1 plus a multiple of 7. So when we multiply 70 by 2, multiply 21 by 3, multiply this 15 by 4, they add them up together, then it will automatically satisfy the first equation. Yeah, because these two, 21 and 15, are 0 modulo 3. So multiplying 2 by 70 will be equal to 2 times 70, and it is the same as 2 times 1 modulo 3, it is equal to 2. So in such a case, it will satisfy the first equation, it will satisfy the second equation, and it will also satisfy the third equation. So this method will produce a number that satisfies all the equations. And once we have one number, then that gives us the complete solution. Because yeah, we find that number, and then the solution are all those numbers that is the same of this number modulo 105. Okay. Now in general, actually, we can extend this technique or this kind of problem with the following observation. Suppose that we have a system of congruence equations. So this is a congruent equation. So this system has 3 congruence equations together. So suppose that we have a system of congruence equations where the modulo numbers that we are using, let's call them n1, n2, n3, nk, they are pairwise coprime. So the numbers here in this example is 3, 5, and 7. So these numbers, they are not having any common factor, so they are pairwise coprime. Then we can see that for this system of congruence equations, there must be a solution. And the solution will be unique modulo the product of n1, n2 up to nk. So let us illustrate this statement, this claim, with a more complicated example. So this example, we have a system of 4 congruence equations. So x is equal to 3 mod 4, equal to 2 mod 5, equal to 6 mod 9, and equal to 1 mod 13. Now so if you look at these modulo numbers 4, 5, 9, 13, so they are all coprime. So we don't need them to be prime numbers. So 4 is not a prime, 9 is not a prime, so it's okay. So as long as these numbers, they are not having any common factor, then it's fine. So how can we solve this set of congruence equations? So can we find a certain x that works? So we will use the same idea as before. So remember previously, so we are multiplying the remainder of 3 by 70. So similarly, what we are going to do is we are going to multiply the remainder of 4 here by some magic number. The magic number should be a multiple of 5, 9, and 13 at the same time, and it is equal to 1 plus a certain multiple of 4. So after some calculation, we find that 585 is such a number. So actually 585, it turns out that it is equal to 5 times 9 times 13. So it is a multiple of these numbers. And when divided by 4, then it will have a remainder of 1. Now we will repeat this for each of these modulo number. So this time, when we are talking about the modulo 5, so what number we are going to multiply to its remainder? So the number, the magic number that we want to find should be a multiple of 4, 9, and 13. And the number itself is 1 plus a multiple of 5. So we find that 936 is one such number. Actually, this number is 4 times 9 times 13, and then we multiply this by 2. Okay, so this is one such number. And similarly, for 9, we want to find a number which is a multiple of 4, 5, and 13, and then it is also a multiple of 9 plus 1. Okay, and then we find that minus 260 is one such number. So we don't need always to choose a positive integer. Yeah, as long as it is an integer that has this property, then it works. So minus 260 is a multiple of 4, 5, 13 because 4, 5, 13 multiplies to 260. And then if you look at this, 260 adds up to 8. So minus 260 has the remainder of minus 8, and then it is equal to remainder 1. So it is equal to 1 plus a multiple of 9. Okay? And finally, for 13, we do the same thing. And then we find that 1080 is what? It is a multiple of 4, 5, and 9. And then itself is 1 plus a multiple of 13. So using the same technique as before, what we are going to do is we'll multiply the remainder here by 585, the remainder here by 936, the remainder here by minus 260, and the remainder here by 1080. So after doing some calculation, we find that it is equal to 3147. So the answer, or one particular x that satisfies this, will be 3147. It works. But then, because 4, 5, 9, 13 multiplies to 2340, so we find that any number that is the same as 3146 modulo 2340 will work. And 807 is one such number. So we can actually check whether it is correct. So 807 is equal to 804 plus 3. So it is a multiple of 4 plus 3. And yeah, using eyeball, we find that it is a multiple of 5 plus 2 because 7, right? So when you divide this by 9, what is the remainder? The remainder will be equal to 8 plus 0 plus 7 modulo 9. So 15 modulo 9 is 6, so it is 6. And when it is divided by 13, what will happen? So 13 times 6 is 78. 80 minus 78 is 2. 27 is equal to 1 modulo 13. So it is working. So in that case, we have come up with a value of x is equal to 807 modulo 2340 will be the solution of this system of congruence equations. Now, we just demonstrate how to solve such a system of congruence equations. But then there are some questions I have left open for you to think about. So here, suppose that n1, n2 up to nk, they are pairwise coprime. So the questions that I want you to think about is, can we always find a multiple of, let's say, the first k minus 1 numbers, but then this multiple is also 1 plus a multiple of nk. Now, if this can be done, how can this be done quickly? So you need to see why this can be done and give an algorithm for doing so. Now, it turns out that solution here, the answer is yes, we can always do so. Now, because of this, can you show that the claim on page 8 is true? So what is the claim on page 8? So this is page 8. So why is it true? Why is the set of congruence equations with the property here will always have a solution? So this is the key question for today. Okay, so that's all for what I want to introduce to you. And then I hope that this Chinese remainder theorem is something that is simple. And then, yeah, so I will actually probably make this into a exam problem. Yeah, thanks all for coming. So if you don't have any question, yeah, let's resume our normal class. I mean, not normal, but it's still online. The lecture summary on Thursday. Okay, so see you.